Hello, everyone. Good morning, good evening, good afternoon, depending on where you are. Welcome, everyone, to the next episode of the YugabyteDB Friday Tech Talks for engineers by engineers. And I'm Kannan Muthukkaruppan, co-founder at Yugabyte. And it's my pleasure to welcome Tanuj again, this time to talk about a very interesting topic. So Tanuj, it'll be great if you can both introduce yourself and then jump into the topic. Thank you.
Yeah, sure. Thanks, Kannan. So I'm Tanuj Nayak, software engineer here at Yugabyte. Been here for over 2 years so far now. And my role here is to kind of work on query optimizer execution and anything surrounding that. So query optimizer execution and its neighbors. So today I'll be talking about one project in this field that we did, and that's making distinct queries run efficiently on YugabyteDB. So let's take a deeper dive and figure out and learn how we did this. So in order to do that, I'll set up an example table that stores information about a bunch of students. Only information we care about right now is what sport they play. So we got this table here with ID numbers, people's names, and what sport they play. So let's also create an index on these guys, right? So more specifically, we create an index on sport right here. So yeah, so notice that previously we only showed, we're only showing 5 rows of this table right here. So in reality, this table here has 250K rows. Around 250K rows, and we're just showing the first 5 tuples that we might see here. So if you do a select distinct query on this, what is that going to entail? So if you do a distinct sport, it's going to entail getting the set of all distinct sports that people play. So in this case, the first few of that set might be basketball, boxing, and handball. Now the question is, how do normal databases, or how do normal databases might execute this? So let's first take a look at what the explain analyze plan for such a query might look like. So first we have an index only scan at the very bottom in order to access every row, and it's going to feed every row into an aggregator above it. And in Postgres or YSQL, we call this unique node. This unique node aggregates every row that's fed into it and uses maybe like a hash table or some sort by distinct aggregation in order to filter out any redundant rows and only get a distinct set of all the rows that are fed into it. So in action, this would kind of look like you got your scan node that reads every single row and feeds that up to its unique node, as I mentioned. So then one may ask, hey, so if this table had 1 million rows and only 5 sports that people like to play, think about it. There aren't the ratio of number of sports people play to the number of actual people in the world. It's not that big. So then one might be asking hey, so we're having to access so many rows, we're having to read so many rows from disk in order to get a very small result set. Can we do better? So maybe we could do better if there's a different method of scanning our tables. Let's just say there was a distinct scan access, a method where, you could kind of, once you're on, say, basketball, once our iterator is on basketball, what if there's a way to skip all future or subsequent entries of basketball and move on to the next sport in order to do kind of what some may call a skip scan? So maybe it would be pretty cool if there's a way to skip around to all the distinct sports in our current data set. Turns out in Yugabyte now, there is a way to do that. And that's our alternative to the traditional index scan called the distinct index only scan. So right now, if you might do an explain analyze on the same query, you might get this exact query plan where instead of an index-only scan, as previously seen, you have a distinct index-only scan that still feeds into a unique aggregator that we'll talk about later. Now, let's look further into how YugabyteDB allows us to skip around a table like this. So the main thing we want to watch out for is our storage layer provides an API to seek to a particular row in our index or table. So for example, you can issue a call to seek our given iterator to basketball, 3, and it'll directly take you to the second row shown here. You can also seek to basketball, 1, and it'll take you to the first row there. You can also seek to rows that don't exist. So you can seek to a target key, and then the iterator will point you to the next best row after the target. For example, if you seek to basketball 4, it'll give you the next best thing, which is basketball 5, if you're sorting lexicographically. Now, using this in mind, we can actually implement our skip scan. So instead of basketball 4, if once we end up at basketball 1, we want to determine that we want to skip all future entries of basketball now that we've seen basketball, we can maybe seek to basketball infinity, and that'll seek past all instances of basketball. So that allows us to implement an alternative to the index-only scan called distinct index scan, as you might see in the query plans here. And the differences between the two query plans are quite fun to look at. So the first thing that might jump out to somebody is the execution time. In the first case, we spent around 400 milliseconds, and then we sped that up to 1.3 milliseconds because we're only extracting the rows that we actually need in this case. And you can see that exemplified by the actual row count by both index access strategies. So in the first index access strategy, we're fishing at the whole table, so almost 250K rows. And in the latter case, we're only looking at the distinct sports that are available, right? So you can see that.
Maybe Tanuj, one question. So obviously, like, because you're reseeking and going to the next unique value of the sport by kind of reseeking to this infinity basketball infinity. In cases where there are a large amount of duplicates, this scheme is going to help quite a bit. Are there any degenerate cases where if all the values were unique, sort of like if you didn't have too many duplicates, could there be a small amount of overhead, or that's not too noticeable?
There would be a small amount of overhead because, again, you're going to be doing seeks here instead of next. So traditionally, if all the tuples in your table were unique, you're better off just iterating through every single row via just a series of next.
Yeah.
Whereas over here, we're going to be trying to seek to every subsequent tuple.
But now, presumably that's a trade-off that as more and more work happens on our cost-based optimizer, we can choose between these two plans. Exactly.
Yeah. So our cost-based optimizer that's coming up will allow us to smartly make that decision on the fly, such that you wouldn't have to make that decision, and there should be ways for you to kind of control which one you're going to be using.
Thank you.
Yeah, so there are trade-offs, but in this particular case where you have a lot of different people playing the same sport, this comes out advantageous.
Yeah.
So yeah, okay, so moving on, let's now jump to why we still need the unique aggregator node, even though the distinct index only scan supposedly only scans whatever we need. So in order to delve into this, let's consider a case where this whole sports index was not on one single tablet, but on multiple different tablets. So let's just say they're on 2 different tablets and we split across handball. And how these tablet scans usually work is our scan access method first scans one tablet and then the other, or it might scan the 2 in parallel. So in this particular case, let's just say it scans tablet 1 first, right? So our distinct scan access method will be tasked with getting all the distinct sports from this tablet. And it's going to give you a basketball, boxing, handball, and it's going to do the same exact thing for the next tablet, right? So then the problem is we selected handball once in both tablets. Someone is going to have to disaggregate those out. So that's why, so in these multi-tablet cases, we would need that unique node there. But, the nice thing is like, the unique node is only needed for those like edge of tablet cases. So the unique node is doing much, much less work than it did with the traditional index only scan. So you can actually use this in any Yugabyte version starting from 2.19.3, and it's on by default. If you ever want to turn it off just to see, maybe the gains you're getting from using this optimization, you can use the GUC to control whether or not this new index scan use method is used. And GUC is on your screen right here, YB enable a distinct pushdown. I'll demonstrate it soon as well. And these distinct index only scans should show up in almost any traditional distinct usage case. Moreover, if your distinct targets are a prefix of an index key you want to use, this is going to show up for you. So in this case, let's consider maybe another example where we have some sort of table 1. It has columns C2, C1, C3, doesn't matter what data type they are, and you create an index on them, right? So create an index on C1, C2, C3. Any distinct on C1 or C1, C2, C1, C2, C3 will benefit from this change. And of course, this works on joins too. So if you're doing a select distinct on any suitable targets from A join B, where A and B are 2 different tables, it's going to work there too. And our query optimizer has been adjusted to be aware of this new index scan method. Now let's think about the opposite case, where maybe distinct index scans might not show up, where one might expect it. So right now, distinct index scans are not supported in conjunction with a few different query constructs, such as non-index filters or aggregate functions like count distinct, or window functions, or distinct on. Now, I'll delve further into the first bullet point, non-index filters, by taking our running example and adding a little where clause to it with a non-indexable filter onto it. How these filters usually work, in this case, we got square root ID greater than 1, is we first extract every row from disk, and then after we've extracted that row from disk, we apply our filters. So if you have a non-indexable filter like this, traditionally you might be extracting way more from the disk than what you're actually going to output, depending on the selectivity of your filter. Now, in this case right here, let's just say we allowed our non-index filters to run in conjunction with our distinct scan access method. Let's see what problems we might run into. So as we might know by now, our distinct scan access method is going to give us we expect it to give us basketball 3, boxing 234, handball 6, because these are distinct rows that pass the where filter that we have put out. But our little distinct node in its method of operation will first go to the first instance of basketball, and then go to the first instance of boxing, and then go to the first instance of handball. So this might be kind of an issue soon, because once these rows are passed onto the YSQL layer, or wherever this filter might be applied, we're going to get rid of the basketball row because its ID column doesn't pass our where filter. And now we're going to be left without a basketball row. So that's going to be a problem. And this is the primary reason why we don't support non-index filters with our new distinct optimization yet.
And I guess in this case, we could have tried to reseek back to, say, basketball with a slightly, to the point basketball one, a point that's greater than basketball comma one to find another. But that's a trade-off, like whether in this case, because the filter is not being pushed down, I think because of the trade-off we are making and staying to the default Postgres plan of just using a regular index-only scan rather than a distinct index-only scan.
Yeah. Also, hypothetically, you could implement this with a bit more work. Maybe instead of going to the first instance of every sport, as soon as, let's just say, we maybe seek to basketball one, we first check if it fits our filter. If not, move on to the next instance of basketball, right? And if it does fit our filter, then you can move past all subsequent instances of basketball.
Yeah.
So this is not a theoretical limitation. Rather, it's just maybe the next step in our optimizations right here to support all these constructs in conjunction with our new scan method.
Yeah.
Cool. So that's all for my presentation. And now let me give you a small demo. Okay, so just open up my terminal window right here and got a 3-node cluster with a table here called T1, right? And it has 4 different columns, it has 4 different columns, and I made an index on 3 of them, right? So let's see what, also, this table has 1 million rows, and for each value of C1, it has about 100,000 rows. So in this case, you can see it has 100,000 rows where C1 equals 2. Same deal for every other value of C1. Perfect setup for a distinct query. So I'm going to set our optimization to false just to show what the query looks like before optimization. So using the traditional query plan, we get a unique node on top of index only scan. Takes about almost 1 second, 971 milliseconds, and it extracted every row from disk. Now, let's turn our optimization back on via the GOC flag I was talking about. And
so in this case, there are only 10 distinct values of C1, right? Because each C1 has 100,000 rows.
Yeah. Well, looks like 11 rows are output actually.
Sure.
Yeah. So let's run the same query with our optimization on, and it runs in 0.5 milliseconds instead, right? And it outputs the same set of rows. So that's.
So one question here, Tanuj, does Postgres, vanilla Postgres, have any optimization like this, or this is strictly a Yugabyte enhancement here?
Vanilla Postgres doesn't have an optimization like this yet. If you might browse some Postgres forums, there are talks of maybe doing something like this, but none of it has actually gone into fruition there.
Okay, thank you.
Yeah. So that's my demonstration and my presentation.
Actually,
I'd love
so
to take
given that you are on that screen, a few other questions. One is like, I'm reading from the LinkedIn channel once again. So although count distinct aggregate is not supported, can we benefit from the distinct push down if we run select count star from select distinct C from foo? So firstly, is it true that the count distinct aggregate is not supported?
Yeah, it's not supported yet. That's just one of those things that might require a bit more work. But let's try out this query that was requested. Oh, sorry. So you can kind of simulate a count distinct by doing the query in the chat.
As a nested subquery, got it. Yeah, that's cool. Thanks for that question. And it would be nice, I think, if we just automatically handled it, but it is good to know.
Yeah. Again, it's not theoretical limitation, just a bit more work to do.
Yeah. So this runs in 0.6 millisecond, 0.59 milliseconds also.
Yeah.
I had one more question. You talked about the C1, C2, C3 case and this code path, this new execution plan benefiting if there's a left prefix, like you do distinct on C1, distinct on C1, C2, and so on. But I would imagine that even if I just did a distinct on C2, technically this idea, if a particular C1 had lots of duplicate C2s, wouldn't and this one is not specific to select count star, but yeah, we can wrap it in. Okay, so we are benefiting from
it works on select distinct C2 as well.
Okay.
Only thing is, when you reach a storage layer, this select distinct C2 gets translated to distinct C1, C2. Then we do some filtering up above. So there's still a huge benefit. I'll demonstrate that right now. But there's some more background work that might go into it. So again, select distinct C2, again, takes almost a second, whereas it took less than a second. Yeah.
Yeah, just 1 millisecond almost. Yeah. You're still getting 1000x in this case. Yeah, that's good to know.
Yeah.
And so future work coming in this is mostly around handling some of the cases like the select count distinct and predicate pushdowns and things like that, right? More cases. Yeah.
Having this run with more things. Yeah.
Another question is, is it specific to distributed tables, or it helps with the co-located table case also? I think it's independent of co-located or not, but I'll let you confirm that.
Yeah, definitely. Regardless of what your table setup is, you're extracting way less rows from the disk, regardless of where those rows are.
Wonderful. And you might have mentioned it in the slide, but which release is this capability available since?
So this is available from 2.19.3. So
okay.
If you're running 2.20, you already got it.
Cool. Excellent. Thank you. Thank you everyone for joining. We finished well ahead of time, but that's a good thing. And see you all next week on another episode of YugabyteDB Friday Tech Talks. This is here, the presentation is simple, but as you can imagine, building some of these building blocks in the code is really cool, and it's in-depth work, and it's want to call out Nayak, one of our interns who also contributed to this, and Tanuj for working on these capabilities. So it's really good to see that. And Tanuj, over to you for any closing comments.
No closing comments, but love to see improvements like these, and this is what we work for at Yugabyte.
Wonderful. All right. Thank you, everyone.
All right. Thank you.